All right, so section 3.1 talks about basic concepts of probability and counting. So it says here in chapter 2, we learned about the descriptive branch of statistics. In this chapter, we're going to begin to study about something called inferential statistics. A big part of inferential statistics is probability or the likelihood of a certain event to occur. So we have something called a probability experiment. It says a probability experiment is an action or a trial through which specific results are obtained. An outcome in a probability experiment is the result of the single trial, and an event consists of one or more outcomes that is a subset of the sample space. Events are typically denoted using uppercase letters. And it says the sample space is the set of all possible outcomes of a probability experiment. So let's see, it says, for example, consider the probability experiment of rolling a die one time. My sample space right here, let me get my pen, there we go. Okay, my sample space is right here. When I roll a die, we can end up with either a 1, 2, 3, 4, 5, or 6, right? So here's what a die looks like. A particular outcome would be, we're going to end up, when we roll it, we get a 3. And then an event might say, what's the probability that we're going to get an even number, okay? So out of these numbers here, which ones are even? Well, it can end up with a 2, 4, or 6, right? Okay, so the first example here says a probability experiment consists of tossing a coin and then spinning a spinner with 4 equal sections of the colors blue, green, red, and yellow. Okay. It says determine the number of outcomes and identify the sample space. Okay, so we can get either, let me get my pen going again. There we go. Okay, so we can get either blue, green, that's supposed to be red, or yellow, okay? So we're going to figure out what is our sample space going to look like. So remember, the first thing we're going to do, we're going to flip a coin, and then we're going to spin this thing. So one way we can do this, guys, is there's something called a tree diagram, okay? So a tree diagram might look like this. When we flip our coin, we can either end up with heads or tails, right? Now, if suppose we flip a coin and we land on heads, then we're going to spin this thing. So once we land on heads, we can either get blue, green, red, or yellow. And if we flip our coin and we land on tails and then we spin the spinner, we can still end up with blue, green, red, or yellow, okay? So we're going to find our sample space. So look, we already started listing it. We can get a heads and then blue. We can get heads, then green. We can get heads, then red. We can get heads, then yellow. Or we can get tails blue, tails green, tails red, and tails yellow. So how many different outcomes do we have? 1, 2, 3, 4, 5, 6, 7, 8. There's a total of 8 outcomes, okay? All right. So next problem here says a probability experiment consists of rolling a die and spinning the spinner above. This one right here. There we go. How many outcomes are in the event B of rolling an odd number and then landing on yellow? Okay, so we're looking for this particular event B. We want to roll an odd number. So when we roll an odd number, that means we can get either a 1, 2 is not odd, Omar. Come on, there we go. We can get a 1, a 3, or a 5. And then we want to land simply on yellow, okay? So how many outcomes? There's 3 of them, right? We can either get 1 yellow, 3 yellow, or 5 yellow. That's that particular event, right? So guys, again, one thing I want to point out, remember when I'm doing this, let me see, let me get this here, and I'll tell you what I'm going to do. Over here to the side, I'm going to say, okay, what would my entire sample space look like? Remember what my entire sample space would look like. 3, 5, 6. Okay, so remember, I can either get 1, 2, 3, 4, 5, or 6, and then from each of those, I can get blue, green, red, yellow, right? 1, 2, 3, 4. Blue, green, red, yellow. 2, 3, 4. Blue, green, red, yellow. 2, 3, 4. Blue, green, red, yellow. Again, 1, 2, 3, 4. Blue, green, red, yellow. And then same thing here, right? Blue, green, red, and yellow. But we're looking for the specific ones. We're looking for getting a 1 and then yellow. 3 and, why didn't I put a yellow there? But that should be yellow. And why didn't I put a yellow here either? Why am I putting an E? Sorry, guys. And that's why there's those particular 3. But this is what the entire sample space looks like, right? There's a lot of elements in that sample space, right? Okay, so let's see. The next part here says, a simple event is an event that has only one outcome. An event consisting of more than one outcome is not simple. Okay, so simple event has only one outcome. It says, consider the probability of rolling a 12-sided die. So think about that. If I roll a 12-sided die, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? These are all my possibilities, right? The event A, consisting of rolling an 11, there's only one of them, so this here would be simple. Now the event B says, the event B consisting of rolling a die are number less than 5. Look how many numbers we have that are less than 5. There's more than one, so this here would be, oops, there we go, not simple. Okay. All right. And there's something called the fundamental counting principle. And it says, if one event can occur m ways and a second event can occur in n ways, then the number of ways that the two events can occur in sequence is m times n. And extend further to any number of events occurring in the sequence. So it says Neela is trying to decide on an outfit for her birthday party. She can choose between either blue or black jeans, a white, red, or blue blouse, and 3 types of shoes. How many possible combinations are out there? Okay, so she can get 2, so look at her jeans. She has 2 types of jeans. She has 3 types of blouses and 3 types of shoes. So 2 times 3 is 6. 6 times 3 is 18. There's a total of 18 different combinations here, okay? Now it says a restaurant offers an $8 lunch special where you can choose from 4 choices for an appetizer, 7 choices for the entree, and 3 choices for the dessert. How many different combinations are there? Okay, so we're going to say 4 for the appetizer, 7 for the entree, 3 for the dessert, right? And again, I will just pull up my calculator real quick. 4 times 7 times 3, total of 84 different combinations, right? And it's only $8. Pretty good. Alrighty. So the next part here says a bank card consists of a 4-digit PIN. Each digit can be any number from 0 through 9. How many possible combinations, or how many combinations are possible when part A says each digit can be repeated? So think about it this way. We're going to make a 4-digit PIN. So first digit, second digit, third digit, fourth digit. Now, we need to figure out, look, the numbers 0 through 9 are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a total of 10 digits here, right? So in the first spot, I have 10 digits. Each digit can be repeated. What does that mean? That means if I want to choose the number 3 in my first spot, I can choose number 3 again. So I still have 10 digits to choose from each time. All I'm going to do here, my friends, is multiply. 2, 3, 4. There we go. And we have a total of 10,000. Okay. Now part B says each digit can be used only once and not repeated. Okay, so what does this mean? That means I still have 10 options to choose in my first spot. Suppose my first number was the number 3. Now I only have 9 digits to choose from. Suppose the second number I picked was the number 7. Now I only have 8 numbers to choose from. And same thing for the last part. Now I only have 7 numbers to choose from. So again, let me grab my calculator one more time. 10 times 9 times 8 times 7. And we have a total of 5,040 options, right? Okay. All right. Part C says each digit can be repeated, but the first digit cannot be a 0 or a 1. So 1, 2, 3, 4. Okay, so my first digit cannot be a 0, 1. So I can't choose those. That means I only have 8 digits to choose from. Each digit can be repeated. So I can still choose, now my second spot, I can choose any number I want. I can choose 10. I can still choose from 10 different numbers each time, right? And so I'm going to multiply straight across, and I end up with 8,000, right? All right, so let's scroll some more here. And we have types of probability. So it says classical or theoretical probability is used when each outcome in a sample space is equally likely to occur. The probability for an event E is denoted by P of E. And so the probability of E, that's how we read this, says the number of outcomes in the event E divided by the total number of outcomes in the sample space. Okay. And it says probability can be written as fractions or decimals. With decimals, we're going to be rounding to 3 decimal places. Okay. So, let's see. A 12-sided die is rolled 1 time. So again, one thing I want to do, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So remember, this is my sample space, right? Those are all my possibilities. We want to find the probability of the event A, which is rolling an even number. So my denominator here is going to be 12 because I have a total of 12 possibilities, okay? Now we want to get an even number. What I'm going to do is I'm going to circle the numbers that I know are even. So how many numbers did we circle? It looks like we circled 6. So 6 out of 12, we can reduce it 1/2. As a decimal, guys, would be 0.5. Now I'm going to write both of them on there. When you're doing your homework in my math lab, it'll be very specific. It'll say type of fraction or type of decimal, okay? Depending on which one it asks you for, then you'll write the appropriate one. So if it asks you for a fraction, reduce your fraction. Don't leave it at 6 over 12. Reduce it to 1/2. But if it tells you write a decimal, then put 0.5, okay? So if you're doing it and you're like, why am I getting it wrong? It's probably going to be one of those two things. Okay, let's take a look at the next one. The probability of event B. Remember, my denominator is going to be 12 here. Of rolling a 5. So out of all those numbers, how many of them are 5? Just one of them, right? There's only one 5 there. So let me see what's 1 divided by 12. And so it's 0.08 with a bunch of 3s. So again, I'm going to write both of them for now. And again, you'll write the right one when you're doing your assignment, okay? And let's see, probability of the event C, again, my denominator is going to be 12, rolling a number greater than 3. These are all the numbers that I have that are greater than 3. How many numbers are greater than 3? There should be 9 of them, right? So 9 out of 12, I can reduce them both by 3. That's 3/4, or 0.75, okay? All right, so the next part that I have here is something called the empirical or the statistical probability. It says this is based on observations obtained from probability experiments. The experimental probability of an event E is the relative frequency of the event E. So here we go. It says the probability of E is the frequency of E divided by the total frequency. Okay, so it says number 8 says STC is conducting a survey to see how often students utilize the Centers for Learning Learning Excellence, the CLE, right? Tutoring lab. So, it's supposed to say so far. So far, 857 students have been surveyed with the results shown below. What's the probability that the next student never utilizes the CLE? Okay, so we're going to find the probability that the student never uses the tutoring lab. Okay, so the probability of never is going to be the frequency of never. How many people never go to the tutoring lab? 52 out of the total. So the total, two ways we can do it, guys. One way we can do it, we can add it up, or we can look right here and it says so far 857 students. 857. So again, I can leave it like that, or I can convert it to a decimal. Let's see, 52 divided by 857 is 0.061. If I go to 3 decimal places, 0.061, right? Okay. Let's see. Okay. Now, number 9 says, what is the, coming back to the same problem that we have here, what is the probability that the next student has utilized the CLE in some capacity? Okay. All right. So, guys, when we say some capacity, that means that they've used it at least once. Okay. Doesn't mean that they've used it sometimes, rarely, often, or always, but it means that they've used it to some extent. Okay. So there's 2 ways we can go about doing this. If they've used it to some extent, again, we're not specifically saying sometimes, okay? We're saying that they've used it at least once. So that might mean that they go rarely, that may mean that they go sometimes, that means that they go often, or that means that they always go. So 2 ways we can do this. One way is we can say, let's take these numbers and add them all up and divide by 857, okay? So if I were going to take all those numbers and add them all up, so let me do that over here on the side. Let's go 143 plus 212 plus 365 plus 85. Okay? And that's giving me 805 over 857, right? And that would be my probability. Another way I could do this, notice how we came up with the number 805. Didn't we take all these numbers and add them up? We added all of them except for which one? For 52. So if we want to find the probability that they have used it in some capacity, we can always say this is going to be 1 minus the probability that they have never used it. Okay. Now look what I'm going to do. I'm going to write this as 1 minus, I'm going to leave it as a fraction form, 52 over 857. Remember, guys, I can think of this number 1 as a fraction. I can think about it as 1 over 1. And between 1 and 857, wouldn't 857 really be my common denominator? And look at the numbers that I'm subtracting on the top. I'm taking the total, which was 857, and we're subtracting that guy there, and that gives me my 805. Okay? The reason I'm bringing this up is sometimes it's actually easier to do this than to add up a whole bunch of numbers, especially if this table is really, really, really big. Okay? All right. So there's something here called the law of large numbers. And it says, as an experiment is repeated over and over, the empirical probability of an event, or the relative frequency, approaches the theoretical or actual probability of the event. And it says, consider the probability experiment of flipping a coin. What's the theoretical probability of flipping a heads? And it says, okay, so theoretical, when we flip a coin, you can either get heads or tails. So we have two possibilities, right? Okay, 2 possibilities. If we wanted to find the probability of getting a heads, it would be 1 out of 2, right? Because one of the sides is heads. Now it says, now try flipping a coin 10 times and recording the results, right? So guys, I know we're in a pandemic right now, so we're not with each other, but last year when I taught this class, we did this in class, and I had, pulled out I don't know, a quarter or a dime, something like that, and I handed it to Debbie, who was sitting right in front of the class, and I was like, Debbie, would you do me a favor and let's flip this coin 10 times? And I honestly, guys, I can't remember exactly what we came up with, but I want to say that we had something like 8 and 2. It was something like that. It was either 8 and 2 or 7 and 3. And that was just, what happened, right? You flip a coin. We're supposed to be getting something closer to, we should be getting something like, ideally we would get 5 heads and 5 tails. But sometimes you flip a coin, you just get more heads and tails or more tails and heads. That's what happens. And then what I ended up doing was, let me see if I can actually find it real quick. I'm going to pause this real quick, guys, and see if I can find what I'm looking for, okay? Okay, so guys, all I did is I just typed in Google like coin flip simulator, and I'm going to flip a penny. I'm going to flip it 10 times, and let's see what happens. Okay, so if I'm doing this, I want you to notice, let me make sure this is recording. Perfect, okay. So 1, 2, 3, 4. We have four heads this time and 6 tails, right? We would be saying, well, shouldn't we be getting, more and more? And if I flip it again, let's see. Now I have 1, 2, 3, still got 4. Now we got 5, right? Flip it again. Let's see. Now we have 1, 2, 3, 4, 5, 6, right? So again, because this is sort of random, this is what we're coming up with, right? So what all that means is that now there's something called the law of large numbers. The law of large numbers just says that when we flip a coin, the more often that we flip, we're going to be getting closer and closer and closer to that 1/2, okay? And that's kind of what we have right here. So look how many times you're flipping it. This is 30, 60, 90, 120, 150. Notice how they kind of bounce all over the place, but the more that we go out, we're getting closer to that 1/2 mark, okay? So, a couple things about probabilities. Probability of a number of an event is always going to be between 0 and 1 inclusive, meaning it can be either 0 or it can be 1 or anything in between. Probability will never be a negative number. Probability will never be a number bigger than 1, okay? So it says, if we know the probability of an event occurring, must be between 0 and 1, then we know that the probability of event not occurring, or the complement event, is also going to be between 0 and 1, okay? So the complement event, I got it right here, is the set of all outcomes of the sample space other than those in E, and is denoted by E with an apostrophe. We call it E prime, okay? So this is just saying the probability of an event occurring plus the probability of an event not occurring is equal to 1. Let me explain what that part means right there, okay? Suppose we said, what's the probability that it's going to rain, right? And we're watching Tim Smith, and in addition to telling you got to know where Mission is on a map, he says, hey guys, today there's going to be a 30% chance of rain, okay? Well, if there's a 30% chance that it's going to rain, then if we wanted to figure out what's the probability it's going to not rain, remember, my chances are always going to add up to 100%. So 100 minus 30 would be 70%. So 30% plus 70% would give me that 100%, which is the same thing as 1, okay? And that's what this is saying right here. The probability that it's not going to rain would be 100 minus 30. That would be giving my 70. Or the probability that it is going to rain would be 100 minus 70, which will give me the 30, okay? That's all that's telling me right there, okay? So let's take a look at some of these problems here. Guys, these problems are taken directly from your homework, so you'll see problems exactly like this in your homework, okay? So it says, if the probability that an event will happen is P of E equals 0.33, find the probability that it will not happen. So the probability that it will not happen is going to be E prime, and it's just going to be 1 minus the probability of E, okay? So 1 minus 0.33 will give me 0.67, okay? This one is saying the same thing. The probability of the event will not happen. The probability of E prime is 0.59. Find the probability that the event will happen. I do it the same way. The probability that the event will happen is going to be 1 minus the probability that the event does not happen, which is 1 minus 0.59, and that will leave me with 0.41. Okay? Notice my numbers are between 0 and 1. I shouldn't get a negative. I shouldn't get a number bigger than 1. Okay? Things like that. Okay? Let's see. Identify the sample space of the probability experiment and determine the number of outcomes in the sample space and draw a tree diagram. Okay, so let's take a look here. It says determine a person's favorite, whether it's ribeye, fillet, T-bone, or sirloin, and the doneness scale, which will be either rare, medium, or well done. Okay, so what's your favorite steak? We got 4 steaks to choose from. We can choose ribeye, we can choose fillet, we can choose T-bone, or we can choose sirloin. Now we're going to choose the doneness. For ribeye steak, we can choose rare, medium, well done. Same thing for all of these. Rare, medium, well done. Rare, medium, well done. Okay? So it says identify the sample space. Okay. So the sample space, guys, I'm going to write this out. Okay? It's going to be a little long, but I can get a ribeye steak rare, a ribeye steak medium, a ribeye steak well done, a fillet rare, a fillet medium, a fillet well done, a T-bone steak rare, a T-bone steak medium, a T-bone steak well done, a sirloin medium, or a sirloin well done, right? Okay, that's my sample space. And determine the number of outcomes in the sample space. So all I got to do is count. So guys, you can go through and count each one of these, or you could say, look, there is 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, right? So I have 3 times 4, 12. 12 is going to be my sample space, right? The number of items in my sample space. And there's another little piece of info here, and it just says that an event occurs with a probability of, let me see, kind of got erased there, of 0.05 or less is typically considered unusual. Unusual events are highly unlikely to occur. Okay. Alrighty. So now let's take a look at the next part here, and it says the frequency distribution shows the number of voters in millions according to age. Consider the event below. Can it be considered unusual? A voter chosen at random between 18 and 20 years old. Okay, so the first thing I need to do, guys, I need to find my total frequency. So I'm going to take these numbers here, and I'm going to add them all up. So let me turn this on. So let's clear it, and let's start adding them up. So 11.9 plus 8.2 plus 24.1 plus 24.2 plus 19.3 plus 60.7. Okay, so my total frequency I'm coming up with is 148.4. 148.4. Okay, so now we're going to look for the probability of choosing somebody between 18 and 20. So 148.4 between 18 and 20 was 11.9. Let's divide those numbers out. So 11.9 divided, 11.9. Oh, come on, why is it not getting 11? 1, 2, there we go. 0.9 divided by 148.4 is, okay. So 0.08 or zero point zero 0.08, yeah. Okay. And it's saying, would this be considered unusual? So I wouldn't say it's unusual because it needs to be 0.05 or less, right? And this is 0.08, so it wouldn't be unusual. Okay. And that right there, guys, was 3.1.